Hello, everyone. Welcome to today's webinar. I'm happy to have as guests today here Waymo and Jazz from PuppyGraph. PuppyGraph is something I'm personally really excited about, as it enables a new architectural pattern, the so-called graph lakehouse, which we'll be learning a little bit more about today. But without going too deep, in my past, I dealt a lot with graphs. I dealt a lot with maintaining very complex, fragile systems, moving data around to populate these graphs. And I wish I just had some of those Delta features like versioning, some of the durability of just having parquets floating around. And it turns out you can get that. So please welcome with me Waymo, one of the founders of PuppyGraph, and Jazz, one of the founding engineers and solution architect, to talk about this, what I believe is an exciting new development in the analytics space. Hi.
Excited to be here. Yeah.
Yeah, thank you.
So I think I do have some slides prepared for today just to give a brief overview of the Graph Lakehouse. So I think we can just dive right in. So today we'll be talking about unified data, unified insights meet the Graph Lakehouse. And maybe just a quick poll in chat, maybe how many of you guys have worked with graph databases, graph technologies, or maybe are even testing out this Graph Lakehouse currently? Oh, yay! Maybe I started too early. Maybe people are still loading in. But yeah.
Yes.
So clearly, Robert, you understand the pains
I
of graph databases very deeply.
I dealt a lot with graph databases, and one thing that the thing I always connected with graphs is semantics and semantic context, right? And I don't need to tell you why this is specifically interesting these days. How do we get context and semantics, words that appear in different contexts as well, into our stack, right? So even beyond all the stuff I did back then, this is really exciting for today's day and age. Yeah.
Exactly. Yeah, and so the big thing about that is that currently a lot of currently graph databases require you to load in your data separately, and it's kind of creating this great data divide that I think is holding back the data stack. Because as you correctly mentioned, graph workloads are gaining popularity. And as people kind of move towards this data lakehouse architecture, what they can do is they can plop on their SQL engine like Spark or Trino and run their SQL analytics as per usual. But they can't really do that for graphs. And so what they'll try to do is run a graph database in parallel to their data lakehouse. And this split architecture is a huge pain, right? You have to think about how to keep them in sync and how to even get your data from your data lakehouse into your graph database. And so you're running complex ETL pipelines and constantly copying over data. And when you're working with petabytes worth of data, people love moving data. It's a fun time, right? And so another thing is that graph databases also kind of struggle to scale. And you would think because it has graphs in its name, it'll be great for that. But the reality is that most of these graph databases are built for OLTP workloads, whereas a lot of these graph analytics that you're trying to run are pulling in a lot of data and they're trying to run these complex analyses. And those are more OLAP workloads. So once you start trying to scale up, that's kind of when your graph queries will stall, which is also unfortunate because our real-time demands are increasing. So let's say I'm a user trying to buy a product online and I have a toothbrush and I want to find a related product to that. I don't really care that you're trying to run a really complicated graph query in the background. What I do care is that I've been staring at a loading screen for more than a few seconds and I'm impatient. I'm going to constantly refresh the screen, right? And so that's kind
And
of...
just one quick remark, because you're 100% right. I think with graphs, one thing I found interesting is that you have to be really careful, because you end up really quickly in that NP kind of algorithmic complexity domain, that really doesn't scale well as you number up, kind of, right? So that's,
Exactly.
yes.
So you can ask the question, but would it be right? Like, does it have other requirements that you need to meet, kind of thing? And so to get there, you first have to solve the problem of can you run the graph queries in the first place? And then another thing is that there's also that additional layer of latency when you're working with graph databases because you have to wait for the data to load in from your data lakehouse, right? And so maybe you're doing cybersecurity analytics for some reason, um, and for the and you're trying to trace like an attacker, right, and trace their attack path. By the time the necessary context loads in, the attacker might have already long infiltrated your system, right? So you can't defend a system if you have no system left to defend, I guess. Uh, but the thing
True.
is that right, and the thing is that you still want to ask these questions, right? Like, I want to know what products are related to my toothbrush or kind of where the attacker is trying to go in my system, and graphs aren't the problem, so your stack just needs to catch up. And then that's when we introduced the concept of this graph lakehouse, which is a graph engine on top of the data lakehouse, which is a very imaginative name. Thank you. And so what this is it's really simple concept actually. It's basically defining graph structures over your lakehouse tables. And so if you've ever thought your tables look suspiciously graph-shaped, now it's really easy to test out the hypotheses because you can map your tables as nodes and edges, and you'll essentially get this logical graph over your tables. And because you have this graph engine, you now unlock native graph query support. So you'll have access to Cypher or Gremlin, and these are very popular graph traversal graph query languages that have syntax and semantics that really support graph traversals. And once again, we talk about scalability for graph analytical workloads because lakehouses are built for analytics. And now you have a graph engine that's built for OLAP workloads for graphs. And at no point in time did I mention moving any data over. So you can see that the data lakehouse remains as your unified open storage for graph and analytical workloads. And like I said, a lot of companies are starting to move towards this data lakehouse architecture with their SQL engines on top. So you've basically got like half the architecture there. You just have to add a graph engine right next to that. Um, and so,
So just for
mhm,
me to understand,
yeah,
what we're doing is when we're setting up kind of this puppy graph instance, we're
mhm,
not moving any data around anywhere, but we're just on the metadata layer, kind of mapping our physical data that we can still query with whatever query engine we have, that we can still write to with whatever query engine we have. And we're just mapping that on the metadata layer into a puppy graph, which then has kind of the query engine, which can run
mhm.
these deep. I mean, once you
Yes.
go deep with the path, right? That's when you
Mhm.
don't want to do SQL based graph traversals anymore, right?
Yep, you've summed it up perfectly. And so what we'll do is we actually connect directly to the data source. And so when we decide we need to pull that data in, then that's when we pull in the data. So we only touch the underlying files when necessary, kind of thing. And I make it sound really easy, right? We're like, oh, we just put a graph engine on top of your lakehouse. But the thing is that maintaining performance at scale is really something you have to consider because we're saying, hey, we want to traverse these tables efficiently as if we had a graph, right? And so that's when the components that make up your graph lakehouse are actually very important. And that's why I'll actually also go over some design decisions in Delta Lake and Puppy Graph that kind of lend itself to this efficient architecture. So we'll start off with Delta Lake that will serve as the foundation for reliable data lakes. Robert, you're a contributor to this project, so you'll probably know a lot more, but I'm just going to do kind of a brief summary. This is not exhaustive, but Delta Lake, Delta Lake will provide the asset transactions that you're used to working with if you're familiar with databases. And they also have this time travel option that, if I'm not wrong, it's because there's a transaction log that keeps track of all these different transactions. So you know your table state at the exact point of time. And let's say you really wanted to travel 7 years back in the past for some reason, you can do that as long as your retention log configurations allow for it. Um,
There's that, yes.
Exactly. The only caveat, really. And then there's schema enforcement, so bad data won't enter your tables, and schema evolution, so you can flexibly evolve the table schema as you go along. Delta Lake also makes it really easy to optimize your data layout. I think you only need like one SQL query to do like Z ordering or liquid clustering to take advantage of the data locality as you're trying to run these large scale analytics. And then Delta Lake also lets you do efficient metadata management. So instead of with data lakes where you have to list out all of your Parquet files that ever existed, you can kind of look at the Delta Lake metadata to say, hey, maybe I don't need to touch this Parquet file at all without even having to pull it in because IO processes are slow. And once again, going back to this transaction log, it provides this single source of truth for both your batch and streaming engines. So it greatly simplifies your architecture. And it's really interesting for streaming as well, because you know what files you have at a given moment. So as new data comes in, you can focus on just processing that new data. There's also the Delta Universal Format, Uniform, that kind of lets you interact with your Delta tables, iceberg tables, and Hootie tables all around the same. So it's great for interoperability and the data lakehouse architecture. And so with that, we move on to PuppyGraph, a graph query engine for the graph lakehouse. Otherwise, you just have a lakehouse. And so, like we said, PuppyGraph kind of introduces this idea of zero ETL with no data duplication because we're able to connect directly to your data source. And then we also offer flexible graph views because you're really just defining a schema.json so we understand how you want your tables mapped to nodes and edges. So if you're like, okay, like at the start, this table is better off as a node, you can do that. And then later on, you say maybe it's better off as an edge. Sure, you just have to edit that one file. And then we're also optimized for columnar storage, which is great because Delta Lake stores stores the data files underlying as Parquet files. So we're really able to leverage that and avoid kind of pulling all the rows in at once. And we're also a distributed MPP query engine, which means we take one big graph workload and split it into little tiny worker nodes to run in parallel. Um, and then we also do vectorized evaluation. So we're kind of able to process large amounts of data at once instead of just going row by row. And we also do query optimizations for graph specific with the cost-based, role-based optimizations. And also we use graph-specific operators that are really built for graph traversals and these manipulation semantics. And then we also offer multi-language support, like I said, Cypher and Gremlin. If you're doing graph analytics, you'll probably run into these languages quite frequently. And on the right, we have a little sneak peek. I have a little Cypher query that I'm going to be running later, so I'll talk about it more later on as well. And so now that I've kind of gone through how Delta Lake and PuppyGraph lend to this graph lakehouse architecture, this is kind of how it all stack up. So you have your stream data coming in and your batch data coming in, and they all enter your cloud storage where they're stored as your Delta Lake tables. And then we have that meta store for that additional layer of governance. And for the graph definition, once again, you just give us your schema.json file so we know your tables map to nodes and edges. And then when the time finally comes to execute the query, we'll take in your Cypher or Gremlin query, create a logical plan from there, do the optimizations, create a physical query plan from there, do the optimizations, and then kind of split the workload across the compute nodes so they go fast. And then you get your results. Yeah. So this is where the animations came in. I like spent way too long trying to align it, but graph database, no, you now have a graph lakehouse.
Yes.
So yeah, it was really worth it. And then so just to
It
summarize,
was
mhm, thank you,
100%.
100%. And so just to summarize kind of what this does, you now have this foundation for zero ETL graph querying with PuppyGraph and Delta Lake because PuppyGraph can directly connect to your Delta Lake tables. So no data movement at all, no duplication of data either. And then because of these design decisions, we offer petabyte scale performance. So even as your data scales up, PuppyGraph can scale with it because we are a distributed query engine. And we greatly simplify the architecture because your Delta Lake tables remain as your single source of truth. And then you can plop in your SQL engine or your PuppyGraph graph query engine and kind of decide which one works best for your use case, which allows you to unify your data and unify your insights because you can continue to cram all your data into your data lakehouse. And having all your information in one place is always really helpful for analytics, because now you get to really explore the context and relationships that exist within your data. So yes, and then we're gonna move on to the demo architecture for the demo I have prepared for today. So we're using PuppyGraph for the compute layer, Unity Catalog for the catalog layer, um, Delta Lake for the open table format, and for the storage layer, I'm using my local machine. But if you're ever planning on releasing this in production, do not use your local machine. It is just a small demo. And then so we're working with the cybersecurity data set today, and I really like talking about cybersecurity when it comes to graphs because you really understand like, wow, it's hard to map all these complex paths, right? And so nothing's more complex than a network infrastructure. That's hyperbolic, but yeah. So we're going to be modeling a network infrastructure as a graph today, where you can identify potential security risks like public IPs exposed to the internet, network interfaces not protected by security groups, rules granted with excessive access permissions, and security groups with overly permissive ingress rules. And this will all be available on the PuppyGraph GitHub as well. So you guys can play along with it later if you would like. Oops. And then let me just change my screen to start sharing the demo that I have. And how do I window? Amazing. Yes. So, oh, where did it go? Uh, yeah, so I very nicely rendered the markdown file so it looks nicer. Um, but the prerequisites is having Docker and Python, and I've actually gone ahead and converted my CSV data to Parquet data already. And so for loading the data, oops, I was running a demo just now. Um, but we'll actually do a Docker compose up and we'll see that we have 3 containers started. So we have the Spark to actually create the tables and load the data in, Unity Catalog for that metadata management, and PuppyGraph for the graph query engine. And then we're actually going to register our tables under Unity Catalog. So you can see I'm using the Unity Catalog open source CLI tool. And I'm just calling my catalog PuppyGraph, and the schema is demo. You can name it anything you want. And then we're going to populate the database now that the tables are registered nicely. So then I'll just show a little bit of the SQL as well. So we're creating the tables in this.
Just while you're talking, I'm really sorry, but I now feel reminded of the hours I spent writing, I don't know, Python scripts that would load SQL tables, transfer it into something I can ingest into a graph system.
This is
Yeah,
traumatic for you, like
that wasn't fun. No,
flashbacks.
that wasn't fun. I just the
Exactly. I was like,
memories coming up.
when I was writing this demo, I was like, what's the easiest way to let people load all of this in? So this is what I came out with. You can ignore all the warnings as well. It's because it's treating this like, oh, it's a database, but it's actually a file path. So things still load as per usual. And then we'll see over here, it's quite cool actually, that these are the tables I've created, and you can see the Delta logs over here that's been keeping track of all the transactions that have happened to that table as I'm loading the stuff in. And so that's with all the tables created and everything, using the Delta table format, and I've loaded the data from my Parquet files. And so now we can just head over to the local host, which means that I have to switch my screen again. Thank you, Carly, for managing all of this stuff. Let's see. All right, perfect. Yay. And so by default, the credentials are puppygraph and puppygraph123 for the password. And then once we sign in, this is kind of where you'll actually upload your graph schema. And so there's two ways to do this, and I'm actually going to show you both ways. But first, we'll be using the UI builder tool, so we have a visual way of building this schema. So we're using Delta Lake, and I can name the catalog anything. So we're using Unity Catalog, and because of how I've configured the Docker containers, I'll be connecting to the Unity Catalog Docker at port 8080. No personal access tokens, and we have puppygraph for the catalog name. And very easy, I'll just get the storage type from the meta store, and we'll submit that. And now that everything's loaded in, we can start creating our nodes and edges. So I'll select from the users. And then I don't really like the puppy ID in front, so I tend to remove it, but it really is just more of a cosmetic thing. But yes. And then maybe internet gateways. And so I've actually chosen these two specific nodes for a reason. And that's because I mentioned that, hey, sometimes your tables look like graphs. And that's because we have this relationship users can access an internet gateway. And you'll actually see in my database that I do have a join table for this. And it kind of exists to capture these two IDs, right? So that's basically just trying to mimic the relationship that exists between these two nodes. And then so we'll go ahead and submit that. And what we're actually doing is we're now kind of mapping the tables to a graph. And with the graph UI builder, you actually get to have a downloadable schema.json file, so you can keep it and then keep on reusing it for future, so you don't have to do that every single time. So we can let you download your schema, and then here are your vertices and your edges. But I actually have a lot more edges to map, nodes and edges to map, and I didn't want to have to do that all on screen. So
So you
I
prepared something,
I
yeah?
prepared it. I did.
Good
Ignore all the
choice.
screenshots
Good
that
choice.
exist. I know. I'm a veteran. Let's go. But yes. So now we just wait for it to load, and the connectivity details are the same as well because we're still connecting to the same underlying source. I've just added way more nodes and edges, and it might take a while because it's on my local machine. But yes. Mhm. All right, perfect. And then we can kind of get an overview of what our schema looks like based on the schema.json file. And if we head on over to the dashboard, we can also see that everything loaded incorrectly. So we have all these nodes, and then here's a sample graph. And these tiles are actually all powered by graph queries as well. So you can customize it however you want. If there's a query you want constantly running, you can just plop it in here. And then, oh man, how do I?
Just a quick question, because you
Mhm,
may have noticed I'm opinionated. I saw this was Gremlin. Is there a
mhm.
Cypher variant for me as well to populate the dashboard? Well, I know that in general you support both, but also in the dashboard.
Mm, that's a good question.
Ignore
Let's
me.
see.
Just go ahead.
Yeah,
Just wanted to.
Um,
the Cypher dashboard is newly released, so you
mm,
can add
Ah,
those.
nice.
yeah, I think this version doesn't have the Cypher dashboard, but yeah, the new releases will have that. And then I'm going to, so I don't have to switch screens, I'll just copy my code here. And so this one is actually, this query is tracing admin access paths from users to internet gateways. And what you can see is that we're kind of doing this pattern matching where we're saying, okay, what users can access an internet gateway? And of that path, how many of the access ones have the property access level of admin? And the reason why we want to keep track of this is we're saying, hey, maybe this user shouldn't have such high access to an internet gateway, essentially. So we can also do the graph exploration. So I can expand all the edge labels and hey, maybe this, ooh, yeah, and then it kind of lets you see, hey, there are other access levels like this, like maybe write access, read access. So it really lets you just explore your graph as a graph. Yay! And
Nice.
then, and I think this next one actually kind of leverages the graph traversal a lot more. So this one is trying to find roles that have been granted excessive access permissions alongside their virtual machine instances. So what we're doing is we're actually mapping once again the path of roles that allow access to a resource. And we're saying, hey, if this role allows access to more than 4 resources, that's overly permissive, right? That might be a danger. And then we want to find out which VM instances might have these roles, because then they're pretty vulnerable. And so then each of these are actually kind of a graph traversal because you're hopping across your tables and everything. So which VM instance has this role that allows access to this resource? And then when we run it, okay, we can see, hey, these are all the VM instances that might be easily compromised as well. And so, yeah, that's it for the demo. I had to cut down on the queries because I was concerned about time, but yeah, because you can go
But
on and on,
not
right?
execution time though, right? Just
No,
talking
not
about it.
yeah, because the thing is that you can really go on and on. Like, there's so much to explore in a graph that it's like, I was like, okay, I have to stop here. But
But
yes,
this is I think one of the powerful things about a graph is that you can actually start exploring and experiencing your data much more. Exactly those interfaces, right? Usually you're quite quickly at a point where you can produce some of those layouts, right? And this is when people actually start to interact with the data. And I don't know, well, one of the things I got excited about here is, and I realized this as you were talking about it, the speed of iteration that you can have in building up the use case. Because one of the problems I found is that cycle across ETL makes it really hard to evolve things, right? But here I can just build a table kind of on the side, switch the metadata, do a different view, whatever. But it's all kind of happening on the metadata layer, and the physical layer of evolving the data can sort of evolve separately from how I do my analytics.
oh, our host is gone. Oh no.
I'm
But yeah,
coming back. Hi.
welcome back.
I keep on dropping out. This this is not as intended.
Mhm.
But yeah, the speed you can, because I found that getting to valuable insights with graphs is a non-trivial challenge, because you need to iterate, but you also don't want to overdo things, because one of the great strength of the graph is also the weakness, because you can model so much, right? You have so much freedom there, and nailing down like the right graph model, as you mentioned earlier, right? Okay, you can make this a node, but you can also make it an edge, uh, and what have you, right? And having a high iteration speed on top of this is incredibly powerful. Actually, one of the things as you said, I already imagined different teams doing different stuff on top of the data, evolving ETL, and then each use case just maintaining a JSON file that maps kind of into that, and yeah,
Yeah,
let them do their thing.
for sure. And it's pretty interesting too because people are trying to start building knowledge graphs as well now. And they're also really flexible because they contain all your company data. And so you can kind of think about, hey, this works well for this use case, but also this use case, and they're all sharing the same underlying graph. Or if you really wanted to customize it per team, you can just have a bunch of these different schema.json files and just plop it in when you need to. So yeah, we really like this plug and go style approach to graph querying. I think it's really interesting as well. Yeah.
Yes,
Mhm.
absolutely. Absolutely. And they can just say, hey, as you said, well, this looks like a graph. I might just go ahead. And then you get these sort of visuals that you're showing. And I found people are excited about this, right? And then they're like, yeah, but could I now know from this edge or from this node where this relationship is? And if you're lucky, it's just, yeah, let me just update the JSON really quick and we'll have it. If that information exists somewhere, right? But still, yeah, amazing stuff.
Exactly. Yeah, and like with the visual tool, it's a lot easier to kind of see how your data looks like as compared to when you're just staring at rows and columns. That's a bit harder to think about conceptually.
Yeah. As the fields evolve, it's yes. If you want to find relationships, I mean, that's kind of the thing of the graph, right? It puts the relationship front and center. I think that's literally one of the definitions, for me at least, that a relationship is a first-class citizen within a graph system, whereas in relational systems, yeah, foreign keys, what have you, sure, relationships exist as well, but they're a second-class citizen compared to
Exactly,
a graph
and they
system.
have different strengths and weaknesses, definitely, which is why being able to switch between these two modes so easily is also really valuable for a lot of teams as well.
Yeah.
And
Yeah, I can literally go in, run a graph query, and then on the same data run some SQL queries to get additional insights. Amazing. I don't know where we are with the demos and stuff. I did have a couple of more questions that came up.
Go ahead. I finished the
I
demo,
mean,
unless you want to
I
see
just
more.
didn't know. I just didn't know you did, because
Yeah.
you said you can arbitrarily deep with the demos as well. You mentioned that you have dedicated optimizers and stuff like that, that essentially allow you to push down. And I don't know if either of you, both of you, also worked on integrating with Delta kernel, because I've been doing a bunch of this, and one of the things that kernel sort of on a low level does is, at least in my mind, it clearly separates. It only supports you in logical planning, right? It says, okay, here you give me some predicate, and my understanding now is from the Cypher query, you do some optimizations. You probably can derive some predicates that you want to push down into the Parquet scan as well. And then, I mean, how that's ultimately my question is, how was your experience? Because right now I feel like in this scenario, because you can optimize your Parquet read to your heart's content and probably have predicates that, well, go far beyond statistics-based sort of resolution of this kind of stuff, and push this into the read, but that you were in complete ownership of that side of the equation, whereas in, let's say, traditional integration architectures, you wouldn't have that separation, right? You're not exposed that logical planning information, but usually just get data back from the table, which would hinder, I presume, a bunch of the optimizations that you probably apply to when you actually scan the Parquet files.
Yeah, so I think the Delta kernel is very important for us, and we are waiting for every new release. And sometimes we even do nothing, but then our current performance improved just because you guys have a new release.
Well, that's good.
Yeah, so our theory is that we define the basic operator a little bit different than the SQL query engine or Spark. Like we are now define the basic operator like aggregations, joins, and also window functions, this kind of SQL stuff. We're more like we have a node action and the edge action. And then we're assuming every graph query, graph pattern, or graph algorithm can be a combination of node action and edge action. So the input is of each action is either a collection of input nodes or a collection of edges, and then the output is another collection of input and or a collection of nodes or edges, and then all the things can be combined together, and then we can do the rule-based optimization and the cost-based optimization. And then when we fetching the data, we just issue the projection with filter things to Delta kernel. and then we can have sometimes we get the edge, sometimes we get the nose or with attribute or not, and but the in table view it's just like a projection with filters, and then because the other kernel thing is column based, and then we can get it only necessary attributes. Like this is also a long time problem for the graph database, since even it's a design storage design for graph, but it's more like a row based system. So, for example, if uh, person node and all the related attribute will be in the same disk page, and then we load all the data into memory. But you know that when you do the analytic query, most time like you have 100 attributes, maybe only 3 or 4 will be accessed by this query. If it's row based, then it's super easy to auto memory. But for us, we can only access the necessary one, and with projection and filters to the kernel, what's the data we fetched is pretty small, and then even it's complicated,
Yeah.
we can still have a very efficient memory usage. Yeah.
And this is it's a good segue into a question that that came up, because ultimately a lot of these optimizations, you have this one thing that you just can't get rid of, which is the latency towards your remote store, right? And Charles, as you reminded us, right, if we want to put this in production, don't do it on local storage, put it onto S3 somewhere. But at that point, you
Oh no.
He will back very soon. Yeah.
yes,
Welcome
this
back.
quick round trips. I don't know what's happening today, so sorry about that. But yeah, we're talking about S3. So you want to be as efficient as possible at that level, and do minimal work, because that's where you really pay the price, kind of. So based on that, there is a question from YouTube. So under the hood, would this be Databricks SQL warehouses, or does it read directly from S3 files buckets?
Oh, we read directly from S3 file bucket. But the lucky thing is that for the performance side, we do a lot of caching and indexing. And like if you already have the order or Bloom filter on Delta Lake, we can leverage that. And at the same time, when we do something, for example, the caching, and we don't need to always read from S3, since in the from the Parquet file, since because you have Delta Lake, and we know that this Parquet file haven't been updated for a while, and it's already in our local disk or even local memory, and then
Yes.
we know that it's a cache hit. We don't need to read it again, and then since usually when you update the graph, it's not change all the time. So if it's a hot run, we can make it super fast, like a sub-second, and for very
Yeah.
complex query. And then we also have provide a trade-off to our customer. When they testing, they always want the fastest performance. But when really in production, sometimes they want some trade-off, like we only cache the last 7 days data, and then
Yeah.
if you want to access the data last year, we just raw fetch from S3. So the performance will be a little bit take a longer time, like 3 or 5
Yeah.
seconds. But usually they can save them a lot of money. So
Yeah, exactly. Once you save a couple of tens of thousands, maybe you get more patient. Yes.
yeah, so if with this week data, the sub-second, if last year data is 3 or 5 seconds, and their customer is also happy about that. So, but that's all thank you to the features of Delta Lake. Since
Yeah.
the lucky thing is that because we follow the theory of the Lakehouse concept, and usually during our implementation and development, and we will just chat your blog
Yeah.
about the new release. At the beginning, we sometimes for example, we also support Iceberg, and then at the beginning we use the Hive meta store.
Sorry for interrupting.
Yeah.
Just there was this question on LinkedIn exactly to that point, right? You already gave the answer, but how is the Iceberg integration?
Yeah. Well,
So
yeah.
you gave the answer. Excellent is the answer, I guess. But go ahead. Yes.
Yeah, the Iceberg, we are design partner of both Iceberg REST catalog and database open source unit catalog. So we are good friends of both of them, and you guys merged. So and
Yes. Yes.
yeah,
We,
and
we, we, we
also
like we like the open Lakehouse where
yeah.
information and data can flow where it needs to be. Exactly.
Yeah, and also because at the beginning we just use a Hive meta store for some time, and then it's not a
It
good
works.
one. Frankly,
Yes.
it's not a good one. And then we suddenly said, "See, you guys release open source the unit catalog." Then we save a lot of our time to develop some features to work around for the Hive meta store. And now after the adoption of open catalog, and it makes our life much easier.
Yes. Yes. Actually, the good thing is because some of the qualities that Delta gives Iceberg also, and you talked about caching earlier, right? So, and I think while I hope that people who operate data in a serious kind of larger scale don't necessarily overwrite files frequently, at least in a table format, you have the guarantee that this is not the case as per the protocol, and that is very amenable to caching approaches that you mentioned, right? This, which is where ultimately you need to do stuff like that to then get performance. Yes, very interesting.
Yeah. I saw someone leave a comment. Everyone wants fast reads and fast everything until the bill comes back to you. I think that's really funny. You're
Yes,
highlighted. Very
that
true.
is that is
Yeah.
a very true comment. That is a very true comment, and this is also why kind of this graph lakehouse or graph analytics on just on top as a metadata layer of your data is so advantageous, right? Because a lot of the dedicated graph systems have dedicated storage, dedicated what have you, and usually that means higher costs for kind of all of this as you kind of run it and deploy it. And yes, if you can specialize everything down to the storage layer, the file format, yeah, then you can squeeze out a little bit more. But as the bill comes in, as we said in the comments, right, that's where you maybe get a little more flexible.
Yeah. And also since my first job is at a Tiger Graph, and usually is a graph database. Usually the charge on data size, and some of customers have 1 petabyte of data, and even they do nothing, but because you need to load all the data on Tiger Graph, you need to pay for 1 petabyte data. And then
That adds up, yeah.
yeah, it make a lot of potential customer run away. And yeah, so now it's just but it's thanks to the Lakehouse things adopted very fast, and we see that a lot of our current customer already have everything there. And when they
Yeah.
try graph, they can just from a very small cluster. And then if the traffic and the workload is heavier, and then they can scale out. If it's just some simple case, they just maybe one single machine and to fetch the data. So we won't charge for data size because everybody have petabytes of data size now, and we only charge for the compute resources.
Yeah, that makes sense. And that's, I guess, the time we're living in, right? So when you charge a premium on storage, yeah, then that's kind of, you need a good reason. You need a good, I don't know, you need to outperform something significantly in order to say, yeah, this is what I do. And that's gotten harder and harder over the years, because by now a lot of the open source stack, with kind of legions of engineers optimized reading against remote object stores. So yes, you have to pay that latency overhead, but we as a kind of community gotten pretty good at that.
Yeah.
Yeah,
Yeah.
awesome. I don't know if there are any more. I think we do have one more question coming in. So let me just read that off of YouTube, I think. For a startup with less than 50 gigabytes of data, does it make sense to go with an enterprise model? Also, do we incur charges when the cluster is not running or only when it's in use? I guess this is towards your cloud offering. I don't know, you want to maybe highlight or outline really quick, well, just in a couple of sentences, what your cloud offering is, and then we can go into that specific question.
Oh, we have like Amazon Machine Image, the AMI on AWS Marketplace, and also on GCP Marketplace. In this case, you can just start it, and it's charged by AWS or GCP, and the later one will be soon released as well. And then that version is a professional one, and you can just click and pay by hours. And then when you don't need it, you can just turn it off. But your data is still there. Since your data
yes.
so
I mean, that's also, I don't know, because with this system, you can scale to 0, right? Because you don't need the storage, and that's usually kind of when some server needs to be online still, is because it holds on to data. But so eventually, did I get that right? So right now it's Marketplace, which is kind of okay, you run it, but you will be offering a sort of a hosted cloud offering where you just point and click and get your instances. Did I understand that right?
Yeah, but it's not hosted by ourselves. It's hosted by AWS. So it's more like run in your own AWS account. Yeah.
But then I think we still offer on-premise, like, so if people care about like the data moving out of their kind of local stuff, we can just bring the compute to you, really.
Yeah.
So a lot of options. Yay.
Yes, that's a good thing. If you carry around something that can be stateless in and of itself, it gets much easier to deploy this in various environments than if you need to carry that baggage of memory around everywhere. All right. I think we're about at time. I don't know, Waymo, Jas, is there anything more you want to share with us, share with the community? If not, I was very excited.
I think you asked everything, since you are expert. You are expert in this area and have a first-hand experience.
Yeah, but it's amazing stuff. We'll have a blog coming out. We'll just need to dot some I's and cross some T's. We'll let people know once that's available soon, where you can do some of the cool stuff that Jas did as well. Try that in your own home at your own risk, though. All right. Thank you so much for being here. And yeah, it was great having you today. I learned a lot. I'm excited. And yeah. Thanks everybody for listening or watching later on. And have a great day.
Thanks for having us here as well.
Thank you so much, Rob.